Hello, everyone. For our next talk, it's building on Erigon-Based node for Type-2 zkEVM. And speaking with us today, who traveled 20 hours to get here, is Max Revitt. He's a developer. All right, go ahead, Max.
Hey, thanks for the intro, man. So welcome. Yeah, this afternoon I want to explain to you how we modified the Ethereum implementation Erigon to build a client for Polygon CDK L2. So in the presentation, I'm going to cover the following topics. So who are Gateway FM? Like, who are we? Who's the company? I'm going to go into what is a rollup. You've probably heard that a few times today. And what is CDK? I'm going to cover Gateway's product Presto, just in brief. And then I'm going to go into why did we choose Erigon to do this implementation. And then we're going to go through the main two parts of the system that we've built and that we're building. So the bit that we've built already is the synchronizer. So we're going to cover the EVM changes we made. We're going to cover the sparse Merkle tree. We're going to cover the dynamic fork enablement. We're going to look at the L1 and data stream sync, so where the node gets its info from. And then the bit that's work in progress, which is the sequencer. So we're going to cover virtual counters, the witness, executor verification, data stream generation, and then our load testing tool, which is the TX replayer. So who's Gateway? Gateway FM is a team of professionals in the crypto space. We build Web3 infrastructure and tooling. We have expertise in blockchain, fintech, infosec, other industries, and that lets us lend our experience to other people to sort of really help the businesses in the space. So I'm Max Revitt. I'm on the R&D team. I'm a developer. My team is a group of people who've been on the Erigon team previously, so we have good experience with this node software, and we've been building solutions in the space for quite a while now. So Gateway worked with some industry leaders and some names that you will recognize, Polygon, WireX, etc., trusted by these partners. So Presto. So Presto is Gateway's flagship product. This is rollups as a service. So 4 clicks to your own rollup. So private ZK rollups with all of the tooling. So once you've deployed that, you get KYC, block explorers, etc. So kind of, turnkey solution for a rollup. We run these rollups for other people, as well as building the technology that underpins them. So that gives us a unique perspective, and we understand the requirements for a user-friendly and performant client, and how to use this client with our Presto users. So having that R&D department also means that we produce a better product in Presto. So what is a rollup? A rollup's a layer 2 scaling solution. It will reduce costs and increase throughput by processing transactions away from the main blockchain. So when it comes to ZK rollups, there are a few types, and they each come with their own trade-offs. So a type 1 is essentially Ethereum compatible. It is basically running the L1. The issue here and the trade-off is that proofs can take a long time to generate. So realistically, that might not be the option that you want. Type 2 has minor changes. So state tree modifications, changed gas costs, some small EVM changes. This comes with the benefit and the trade-off that you get quicker proofs, but you may encounter some incompatibilities when trying to run your smart contracts. We then move to the Type 3, and again, the trade-off towards performance is most heavily skewed here, so it's mostly Ethereum compatible. You've got fast proofs, but you get more incompatibilities. So for example, most of them would be no pre-compiles. So CDK is a Type 2 rollup, and throughout this, CDK was Hermes Polygon zkEVM, so it's useful to know the terminology and the history, so CDK is the name we'll be using. So the question is, why did we choose to use Erigon as the node to do this? So Erigon benefits from a low footprint on disk. Anyone familiar with the node in the Ethereum L1 space will know that. It's an all-in-one solution, so RPC, transaction pool, EVM, etc. They're all there in one repo to be run. It has a stage-wise sync, so instead of going block by block, the node will sync in stages. So we can optimize some operations for the batch. So for example, in this case, we can verify multiple blocks in a single state root calculation. Erigon uses MDBX, so this has some advantages over things like Bolt and LevelDB in that it's simultaneous read whilst you're writing the DB, which means we can split the parts of the system up, and it's super fast. So as I said, you can run components of Erigon separately. A good example there being that you can separate the RPC out, and it can still talk to the database whilst it's being written, and the sync is happening in the background. So it's very capable as an archival node. And it's an ideal candidate, in fact, for syncing the layer 2. So the first part of the solution that we've provided, and this is the synchronizer, this is a node that will consume and sync the blockchain, and it will allow you to then stand up an RPC. So it syncs from both the L1 and a data stream, which is produced by the sequencer. So the sequencer will produce the data stream which contains transactions, batches, and other data, and then we use L1 sequences and verifications. So the L1 verification will contain a state root which we can use to then check and make sure that the chain is okay. So we made some adjustments to the stage sync as well. So we replaced the headers and bodies stage with a stage which actually retrieves data from this stream and pipes that into the Erigon-DB, MDBX. And we have a new stage which is for creating the SMT. So we replaced the Erigon into hashes stage. And this allows us to generate a sparse Merkle tree, which will give us the state roots. So that differs a little bit from Ethereum mainnet with the Merkle tree. Where possible, we have tried to maintain upstream compatibility. So obviously this is a fork of Erigon. We want to be able to take changes from the upstream as and when they come. So we've kind of added _zkEVM to the file names and tried to, where possible, separate out the code we've written as much as we can, so that when it comes to the actual code files that are already in Erigon and in the upstream, we've made small incisions there. So hopefully when we rebase on the upstream, that's going to be a lot more easy, because we're just going to see like a function name change or something like that, and it'll be fairly clear that, okay, this is the zkEVM version, and we'll know which to take. So also we've added a new RPC namespace. So with this being an L2, there is a zkEVM namespace, and that allows you to get stuff by batch and do some operations like that around the batches. So since we're running a Type-2 rollup, we had to make changes to the EVM, as discussed with the types of rollup. So this is a EVM that's based on the Berlin hard fork. We made various changes to opcodes, so Xcode hash returns the hash of contract bytecode from the state tree. Difficulties returning 0. Static call doesn't override return data, if the execution's reverted. We also have a new type of error for disabled smart contracts, so that makes it behave a bit like an error reverted. With each fork, we've changed the pre-compiles to match the CDK requirements. And we also replaced self-destruct with send all, so this prevents funds from being lost in the L2. This isn't necessarily EVM changes, but there's a couple of things that we have to write into contract storage as we do the execution. So global exit routes are placed in the global exit route manager contract storage, and then the transaction number and state route are each placed into the system contract at that point as well. So the sparse Merkle tree, this replaces the Merkle tree from the Ethereum implementation. And the benefit of sparse Merkle tree, which is a 20-minute presentation on its own, maybe longer, is that we can do efficient non-inclusion proofs. So we took an algorithm that existed from the JavaScript implementation of the node, and we made some performance increases. So as I said, we have the stage sync. Well, that means that we can do a batch-wise operation on this tree. And we added some efficiencies there so that we don't multiply hash nodes. And so we got a huge performance benefit there. We use the Erigon history so that we can incrementally update and unwind this sparse Merkle tree. And luckily we retained DB compatibility with the JS implementation, which was a huge debugging win for us, because we've got a lot of state and we're trying to compare and see why our state roots have differed. So that's been a huge help as we've done the project. We've also added dynamic fork enablement. So normally in upstream Erigon, you would need to know a block height or a timestamp of which a fork would be enabled ahead of time. Here we can code for it and say that it's fork ID X. And when that fork ID is actually enabled by the chain, we'll consume that, and that will set that feature set live. So this is this synchronizer is currently in alpha, and we'll be doing the beta soon. This brings me on to the sequencer. So this is a work in progress, and this is a separate mode of operation for Erigon, where the node will build blocks and batches, which will be sent to the L1. So it acts as the centralized sequencer. Now, this is obviously replacing an existing sequencer, which has a different EVM implementation. So we have virtual counters, which mimic the requirements of the CDK hardware, and they prevent us basically from overwhelming the prover. And the way we've done this is we wrap the Erigon jump table, and so different counts are assigned to different things. More expensive operations will have a higher impact here. And so we're aiming to limit work done by transactions and limit the batch data size. So because proofs are expensive, we want to maximize each batch. So as we go through, we're working with these counters. And if we hit a counter overflow, we will simply revert back to the previous transaction and then build an optimized batch size. We've implemented the witness. So the witness is a description of changes to state. So it's like a partial sparse Merkle tree. And we can send that to the prover. And we can send that to the existing executor, in fact, for reasons we'll see later. And that allows you to sort of have a stateless reconstruction. And we can use this to verify the existing sequencer implementation, which we're going to see next. So this is where we run Erigon in the sequencer mode. And obviously, once we built a batch, we need to know that our EVM has had the same outcome as the existing executor's EVM. So we actually, we have to keep compatible with the upstream ROM. Due to performance reasons, we use a pool of executors asynchronously, and this is where the statelessness comes in with the witness, so we can verify multiple of those at once. Now, on the happy path, that's great. When there's an issue, we go into like a limbo mode that we're calling it, and so we have to sort of revert the batch to find the failing TX where there's this incompatibility, and we'll remove that transaction from the pool, and then we'll move forward again. So that's how we're dealing with the differences that we may perceive there, and obviously that will be logged, and hopefully the issues will be raised, and we can then resolve that. The sequencer does data stream generation. So at the moment, the synchronizer node we talked of is consuming the stream from the Polygon implementation of the sequencer. At this point, we will start generating that stream for these synchronizer nodes and exposing it. So pieces of the stream are being verified by the executor in that verification step as well. Obviously, whilst doing this, one of the outcomes that we want is a performant node. Performance sequencer. So we built a TX replayer, which allows us basically to push transactions into the sequencer and replay them, say, from mainnet. And that's kind of like a good real-world test. So to summarize what I've talked about, rollups are a layer 1 scaling solution. The rollup type indicates that compatibility and performance trade-off. CDK sits at the Type-2, so we do get a performance benefit, but we don't introduce massive incompatibilities. Most smart contracts hopefully will work there with minimal tweaking. The reason for the project, the existing Polygon CDK ecosystem is being augmented by this Erigon-based node. I think it's going to be slightly more ergonomic for infrastructure, to run this node. And hopefully we can squeeze a little bit more performance out there as well. We've talked about the Presto ecosystem, so obviously that's gateways, rollups as a service, and we deploy things like this solution to allow you to have 4 clicks to your own private zk rollup, which obviously is super cool and a kind of like turnkey solution. We talked about the synchronizer, which is in alpha. The beta is coming soon. And so that's for running basically your RPC nodes. And we also talked about the sequencer, which is the work in progress, where we're building blocks, batches, and submitting them to the L1. So I'd like to thank you for listening. If there are any questions, we'll be at the Polygon booth for a bit. We talked through quite a lot of deep concepts there in brief, so I'd be happy to go into a little bit more detail if anyone wants that. So yeah, thanks very much.